How was it when you were connecting online? Was it convenient?
Oh yeah, yeah. I didn't have any issues.
Okay.
So it was very nice, and I could see everything pretty well. It was
Okay.
a little fuzzy. I don't know if it was my connection or whatever, but when I looked at the YouTube videos, it was
That's good.
fine. So that really helped me.
Okay. Okay. So I posted a homework too. I changed the pen, thinking that it might be better because some of the students say that it is a little fuzzy. Not that it is hard to read, but I've been doing this for since March whenever this started. Apparently in the spring last semester it was much better, but then it was not on this board, it was on a different board. So one of the contributions probably is the pen that I was using. So that's an experimentation. You'll see. But, let's do. Was the time sufficient for the homework?
Yes. Yeah.
Was it too long, too short?
No, it was perfect.
Okay.
I think so.
Okay. Oh, there is a midterm also, right? It's relatively far. It's March 2. Just a Tuesday. Okay, so we did. I said Newton's like forces. Let's like forces in Newton's law. Very broadly, in a certain kind of classification, you can say force is a constant. Right, and we are also saying it's one dimensional, right? So let's say in one dimension, that means everything is moving along a straight line. That simplifies things significantly. And the second one we said was force being a function of time alone. Third is we said force being a function of position alone. And fourth could be force being a function of velocity alone. So that's x. So this is, of course, uniform gravity. This is a general, we didn't specifically consider much, but let's say non-uniform gravity or non-uniform acceleration. It's just a matter of integrating with respect to time and you get it done. If it's non-uniform and just position of x, a meteor falling is a good example, and we try to discuss that. And in that concern, we did talk about sojourn time. Did you guys look up?
Yeah.
Did you get the chance to look up sojourn time?
Yeah.
And we pointed out that. And we said that sometimes time taken is infinite. Like you wouldn't expect it, like especially the pendulum thing.
Yes.
If you're not familiar with it before, and you would go ahead and calculate, oh, how much time will it take? It would be a little surprised that it never reaches up there. Right. So, so it's good to know that there are divergences, like these are kind of infinities, and divergences of that kind also shown. And of course, there's velocity, and here we will do drag forces for now. And of course, when you go to 2 dimensions, then there is so since it is 1 dimension, I'll keep to drag force, but magnetic motion in a magnetic field is a classic example. But since it is 1 dimension, I will not write it down explicitly here. But we will do that if we get a chance to. So let's do drag forces. So what we are talking about is there is uniform gravity. So drag, let me say drag forces, drag in uniform gravity. So we're saying there is gravitational field down, writing it as a vector, but that's all the motion is happening in that direction. So it's not really relevant. And if you just have one mass, m, there is a force mg acting down, and let's say it is going downward. We can also talk about things going upward and then falling. It's like if you throw a stone up in the air or stone or something with a larger surface area, when it is going up, the drag force is downwards, right? Then it reaches the top and then the drag force changes its direction. Right? So that you have to analyze the problem in 2 steps in particular. So, but let's say it is dropped, initial velocity is 0. So let's say v of 0 is equal to 0. And there is a drag force acting upward. And now there are 2 cases for 2 broadly 2 cases. So case 1 is when drag force is proportional to velocity and with minus, which is b times v. The minus sign here means that it is opposite to the direction of the velocity. If it is a vector, I think best is to write this as a vector. So then it is very clear. So it is opposite to the direction of velocity. And case 2, now that's where the vector sign cannot capture this. And this is equal to minus of again some constant, let's say minus, let's call it, is there a C somewhere? No, right? I think there is a constant. Because in this case, it's very standard. Yeah. D. Yeah, let's say B. Or should I? Or B prime, let's say. C. B squared, where C is, incidentally, it's an empirical relation, nothing deep in here. It's D times rho times A. Rho is the density of fluid. A is the area of cross section. And D is dimensionless quantity. It's dimensionless. This is called a drag coefficient. Pretty much like your coefficient of friction, right, which captures the property of the interface, if you want. But then one can always wonder which one does system know. Like, so two extreme scenarios are, again, these are empirical relations. Two extreme scenarios are, let us say, so let's say, what does it depend on, right? So it depends on speed, relative speed, let's say. If you're going very fast, then it is, so this is fast, it's probably v squared. If it is slow, that's v. That's not really a good way to say it, because whenever I say slow or fast, it is compared to something, correct? So I'm not giving those real parameters. For that, we will have to go into fluid dynamics and talk what is called the Reynolds number. Yeah, maybe we usually have a quiz, right? So quiz, so this Reynolds number. Look up what is a Reynolds number. Actually, instead of looking up what is a Reynolds number, I suggest that like this is a way to expose concepts, right? So look up, there is an article called Life in Low Reynolds Number. So whatever I'm saying, slow, fast, and other things is decided by what is called a Reynolds number. If it is smaller than 1, there is a certain kind of behavior. If it is larger than 1, there is a certain kind of behavior. Primarily, if you're in a viscous solution, like imagine you are moving in honey, the kind of techniques you use to swim in honey is entirely different than the techniques you use in water. If we never learn it because we never have to survive in honey. In water, it was necessary because we evolved in water. So we learned techniques to swim in water, for example, in general animals, something. But if you're a very small organism, for example, bacteria, right? They don't use techniques like we do. Like they don't, like what we do is pretty much move the water backward and go forwards. It's like an action-reaction force. The inertial forces matter a lot. The force equal to MA. MA plays an important role. But if you're very small, that is a small Reynolds number, that's what either you're moving very slowly, or if your size is extremely small, think of a bacteria inside of water. It doesn't even have to be viscous. But when it comes to bacteria, you're in a Reynolds number, you cannot really push water and go forward. So if you notice, bacteria have this cilia kind of stuff. So they have this long antenna kind of objects. So earlier it was, or one might suspect that those are for detecting things, those are sensors. They're actually not sensors. They're actually like for motion. And the way they do is they twist their cilia to move forward. It's like, think of earthworm moving forward. So it's kind of a interesting feature. This is an article written by Purcell. It is not really a paper. It is a summary of a talk he gave, a popular talk he gave. But it's a very, how do you say it, eye-opening feature. One never realizes that, in a world that is slightly different, that's how things will go. So that's okay. Very broadly, more strictly speaking, this has those features. So this is very simplistic, but in fluid dynamics, this is more important feature. Examples I meant also the size, right? If size is small, so maybe I should say big, right? Big is v squared. And small is v. Right? Examples help. If you are skydiving, like v squared is skydiving or if your car is on an interstate, like car on an interstate. Those are all reasonably well understood as a V square, and V is if you have a very viscous solution, a high viscosity. Viscosity or bacteria in water. Right, those are general ideas. What I'll do here is the standard thing, which probably you've done in your undergraduate course, is when it's linear and velocity, and in your homework, you will extend that to V square. And if time permits today, I will do magnetic field motion also, which I think we should be able to do. This should not take too long. And then we will start going into generalization of action principle. Okay. So equations of motions for this is mass times acceleration. So let me write this as a vector equation. So that's equal to mass times gravity plus the force of friction. There are only two forces acting, and when I write it as a vector, the sign is included in the vector. So what we have is m times dv by dt, v as a function of time, that's equal to minus mg. And force of friction we set is now in the upward direction because it's opposite to the velocity. So that's plus d times v. D is some constant. Think of currently, notice that we are not doing a skydiving really, but it's like that's a thing that comes to your mind, but this is more of a highly viscous solution, a slowly moving sphere. Like think of a honey and you drop a small metallic, a small tiny object and it will slowly drop down. So this is equal to dv by dt is equal to d times d over m times v minus g. So yeah. Put this together as let's say yeah. So this is d over m times v minus let's say g m over b. Is that what I want to do? No, first let's define something here instead of trying to remember what it is. Yeah. So right here itself, remember that's the acceleration. So now let's define what is called a terminal velocity. So let's define what is terminal velocity. So what is what do you think is terminal velocity? Oh, what is this? I think I don't have to worry now. Yeah. What do you understand by terminal velocity?
The velocity, the end velocity an object reaches.
End velocity.
The max velocity an object can reach when in a certain medium, such as air.
Yeah, and after it reaches, what happens?
I don't think it gains anymore.
It gains, it does not gain anymore. And that would mean that the acceleration is zero, right? So we can set this to zero, right? right? So terminal velocity by definition is where eventually it stops gaining velocity. So dv by dt is 0 then, right? So that means b times e over m, now it's terminal velocity, minus g is equal to 0. That means I have an equation for terminal velocity. That's vt is equal to g m over b. Right. So in terms of, so then we can write everything in terms of vt. So this is convenient to write. So this is b over m times v minus vt. In fact, since b is sort of an unknown here, it's good to write it in terms of terminal velocity itself again. So this is vt over g is equal to m over b. So that's equal to vt over g. Oh, let's define this to be, what will be the dimension of vt over g? Dimension of this?
Sorry,
1 over?
meter.
No, right? G is velocity over time.
Yes, so it's
So it's seconds. So let's define this to be a curve. It's some time, right? So it's a scale in time. So it's good to define, and that's a constant because G is a constant. Terminal velocity is a constant. If once we are specified in B, then there is a special time tau associated with them, and we'll ask about what is that tau very quickly. So this is equal to so is m over b is tau, m over b is tau. Okay, so it's good to write this equation as dv v minus vt is equal to dt over tau. So then that way we are having dimensionless quantities, dt over time and dv over v minus v. That's a simple integral. Notice that very similar argument we will go through when you're doing v squared. That's your homework. Right? Instead of velocity, linear velocity, this will be v squared. This will be v squared here, some constant times v squared. You will still be able to define a terminal velocity. You again say that the acceleration is 0. It will be an entirely new definition because now this is in terms of b, there it will be in terms of c, right? In terms of this constant, and this will become v square minus some quantity, and that it will be defined in terms of v squared, and this will be an integral over v squared. Again, you will be able to define a time there. In fact, it will come out to be exactly the same definitions in them. But the integral from this point on will be different. Again, there is an initial condition we have earlier put, and that is that the 0 is equal to 0, right? That's the initial condition. Initial condition. Complete the integral. So let's do the integral here, and we know that the integral of 1 over v is log. It is log of v minus vt is equal to t over tau plus a constant. And since there is a c there, let's stop our constant. So alpha. That's an integration constant. but we can immediately see what that constant is maybe. Let me first invert it. So this is V minus Vt is equal to exponential of t over tau times exponential of alpha, which is constant again. Exponential of alpha can be thought of as the constant. So now let's say what happens at time t equal to 0. Put in the initial condition at time t equal to 0. What we have is 0 minus Vt is equal to e raised to alpha times exponential of 0 is 1. So we learned that exponential of alpha is minus Vt. So our velocity as a function of time is minus Vt is equal to minus Vt times exponential over tau. So simple solution. So it's 1 minus exponential of t over tau. Where do you see this solution? Where else do you see? Have you seen the solution? Probably. Let's come to that. I'll ask that question again, but let's first plot this. Maybe that will remind us. So if I were to plot this, how will it look like? Like, so what we're saying is that velocity increases or decreases in this form, correct? So velocity obviously increases, correct? So it increases from 0 to some constant value. So let's plot this. So t equal to that's t, and that's velocity as a function of time. Eventually, for large time, exponential is extremely is this correct? Is this right? Well, that must have I say there is a problem because as time increases, this seems to diverge, right? This can grow more than 1. Right?
Yeah.
Yeah, so what went wrong? Let's go back. I think the point is acceleration here, right? When I say v, dv by dt, I am saying that velocity is positive downwards, correct? And then there will be an opposite sign, I suppose, correct?
Yes.
So there is an overall sign difference. Right? So even though I wrote it as vectors there, in my head I'm thinking that everything is positive downwards, but then I wrote it, I didn't take care of that. So overall, this whole thing should, let me just, instead of doing that, so I'll put a negative sign there on the left hand side. Is that clear? Okay. So that brings in a negative sign on the right hand side. So this will be a negative t over tau, and this is can be still plus, no problem. And this brings in a negative sign. And sorry about that. Confusion. And everything stays the same except that this is negative. right? So now let's ask what happens at very large t. At very large t, exponential dies, right? So this is equal to 0. So at very large t, it is the terminal velocity. That's good. So that's your terminal velocity. So at very large t, it reaches terminal velocity. At time t equal to 0, this is 1, 1 minus 1 is 0, so it starts from 0. So somewhere here, this is this, and it grows from 0. So these two have to get connected. Exponential curve, if it was a only exponential of minus x, so that's this, right? So that's exponential of minus x, so that's 1. 1 minus of that is exactly the reverse, so that's your exponential curve. Right. And again, one could ask, at what time, like we said that this will attain terminal velocity. One could ask, at what time does it attain terminal velocity? It is at infinity. It doesn't make sense because it will never reach terminal velocity. It's only approaching. So that question is not really useful for us. So what could be more practical is that we could say, how much percentage-wise does it reach? And that is where you get a scale for time. Right? So tau is at s. So let's make this 1. So at what time is the terminal velocity 1 minus of this? So let's ask, at what time or let's say, no, not at what time, so let's say at t equal to tau, right? So that is at t equal to tau, v is equal to v is how much percentage of Vt. Is that question clear? Like this is, if it was full 100%, then you reach here. But at some time tau, this is maybe 30%, maybe 70%. And that's a scale in time. That gives you a clear reference in time. And that's easy. You put in t equal to tau. So that's, so v is equal, v at tau is equal to Vt times 1 minus of exponential of minus 1. And that's equal to, so percentage wise or fraction, if you want to talk, so that's equal to, this is the ratio, so that's E minus 1 over E. Right? And E is approximately 2.7, so that's 2.7 minus 1, 1.7 divided by 2.7. Right? So E is equal to 2.7. E is approximately 2 6 digits, that's 2.7. How much is that? Have you seen this ratio before? Somewhere? Where have you seen this curve before? So this is this comes out to be approximately 63%. So that's it, and that's 0.63 Vt, right? And tau is called a time constant. like whenever there is an exponential decay, you need, there is a scale associated with the exponential decay. You talk this in terms of population growth or radioactivity, or exactly this curve shows up in a charging a capacitor, right? If you were to charge a capacitor using a simple DC voltage and a resistor, then you get exactly the same curve, except that this will be a voltage now, and tau will be given in terms of resistance RC circuit. So yeah, RC circuit actually gives you exactly the same equation. Time has the same interpretation there, but instead of velocity, you're talking about voltages and current. Current decays there. This is the voltage. Okay, so that's something. And again, the time here also we can talk about the acceleration also, right? So remember, derivative of charge is current in RC circuit. So derivative of velocity will be acceleration. So that is a one-to-one connection there. And your homework deals with V square again. Okay? So you have to pretty much analyze the same thing for V square. Okay, any questions? Comments?
Yes, so in terms of like the electrons in a wire, they experience a drag force.
Actually, that's not the reason. Yeah, okay, good point. Yes, they experience a drag force for sure. That's why, I mean, even though the electrons are going extremely fast, like almost at the speed of light, but it takes forever for the electron to reach from here to there. They go extremely slow inside a wire on an average. But at an instantaneous speed, they are going at speed of light, but they keep going around. And they do experience drag force very much, but that's not the reason why you have RC circuit time constant. Like the differential equation there is, let's see. So what you say is you have a battery, right? And then a resistor, and then you have a capacitor. So yeah, maybe you're right. Okay, yeah, you might be right, because it's just that resistance is a drag in a sense,
right?
Yeah, so probably yes. I think so. So let's see. So you would say this is, so let's see the analogy here. So you would say, so there the equation would be V. So this is the V. That's the resistor R, and this is C. Correct. So voltage, which comes out to be a constant. This is equal to IR. Right? And this is equal to plus Q over C. And then you would say that, oh, current is dQ by dt. Right? So this is V is equal to R dQ by dt plus Q by C. No, there is a difference here. Let's see. Okay. So now let's rewrite this. Right? Let's rewrite this on the left. So this is dQ by dt. So that's equal to minus Q over RC and plus V over R. Okay. So notice the comparison. Now this is like inertia. Like this is, let me compare it with this, right? So this is dV by dt is equal to minus B over M V plus G. And notice that you were correct in saying that so this is the resistive force here, right? But that is actually the driving force in this case, in a sense, as far as charge accumulation goes, that is actually helping it, and it is the capacitor that is doing the, at least relatively speaking, if you go by analogy, exact analogy, capacitor is doing the job of the resistance. It is like saying, I think the point is that if you have a lot of charge on the capacitor, then it doesn't want anymore. And how much charge there is on it decides how much more it will take. Right? It's like a population. If you already have a lot of population, then it doesn't want anymore. So it is less increased in a sense. So yeah, the dynamics of that is slightly different, even though yes, the same drag there. So it's not drag at all. So equation-wise, there is a similarity, but conceptually, it's not the same identical. But of course, there is a drag inside that, but it's just that in this particular phenomena of RC circuit, that's not playing a role. Good point, though. It's easy to think of it as, oh, while we're talking about drag, there is a drag resistance, of course. Yeah. So it's the same. Thank you. Yeah. Good. Yeah. Okay. So that's of course the drag force, the most classic velocity dependent force is the magnetic force, and it is a fundamental force. So let's talk about motion in a uniform the charge in a uniform magnetic field. So again, we should have seen this in some undergraduate course. Let's say this is the magnetic field coming out of the board. Let's say B coming out of the board, and let's say we have an axis like this. That's your x-axis, and that's your y-axis. For convenience, let's choose this magnetic field to be coming out of the board, and it is in the z direction. And yeah, I usually ask whenever in this manner. So, is there a choice we have of z? Does the z come out of the board or go into the board?
I say coming out.
Is there a choice? So if I have x-axis here, y-axis there, is z coming out of the board or going into the board? Or yeah, there is a right-hand rule. So good. So or we use a right-handed system consistently everywhere. But a left-handed system is possible, but then the physics could be different out there. So okay.
So let's specify a problem. So we have magnetic field chosen to be in the z direction, and it's uniform. So it is 0 I plus 0 j plus 0 k bk. Like IGK is x. Sometimes I write x hat, y hat, z hat. Yeah, actually the same page I wrote on. So z hat and k hat are the same. So I keep interchanging them. Here. Okay. I have. So let us say that it starts from the origin. So x at time t equal to 0. Right? Always we need an initial condition. X at time t equal to 0. That's exactly at the origin. So that's 0. So that's your position of the, and let's say it's a positive charge. So it's a positive charge right at the origin. Let's also say that velocity of the charge is equal to 0. Right. What happens then? Let's say if you keep a positive charge at rest in a magnetic field, what will it do? It will speed up. It will speed up. Try again.
It will not,
It will not. And why not?
because it's not moving with any velocity.
Yes. And so what is the force? Because the force is equal to magnetic force is equal to QV cross B, right? That's the equation we have. So if velocity is 0, it doesn't experience any force at all, right? Right. To begin with, it should have some velocity. Unlike electric field acts on a charge even if it is not moving. Magnetic force doesn't sense a charge if it is not moving. So if you want to escape magnetic field, just to go stay still. And the moment comes, what do you mean by still? It is always relative, right? So we'll come to that later in an E&M course somewhere, that magnetic field is a relative concept, like Einstein's theory of relativity. Who is moving is important. So magnetic field is not a does not have an absolute meaning. So it depends on the reference frame. But all this is with respect to the lab frame. So this is not an interesting problem. So we have to change this. Right? Equal to 0 is not interesting because it will just stay at rest. So we have to use some motion. And to begin with, let's say this is 0I plus it has some initial velocity j plus 0k. Right, that's your motion, and that means it is in the beginning moving in this direction. And I chose that to be in the j direction. If that is the case, what happens to this charge? What happens to a charge in a magnetic field? Eventually, what is the motion typically? Yes? Yeah. It goes in a circle, right? Yeah, it actually goes in a circle, which is not very obvious. That's what we want to show. But it's very clear that if this is the force, V cross B, B is coming out of the board, so there is a force in this direction. But the moment it changes its direction, the force also changes its direction. So it seems like it starts going like this, and the statement is that it actually goes in a circle. But then we should be able to show that it's actually the path is a circle, and that's what we will try to do. Okay. So mass times acceleration is equal to Q V cross B. if something is going in a circle, and especially with uniform velocity, then or uniform speed, then there are two definitions that comes in. One is how often is it going in a circle, like how fast is it going in a circle, like a time period of the rotational motion, and the second is the radius. Right? There are two properties of circular motion. One is the angular frequency, and the other is the radius. So let's see. So this is dv by dt can be written as this is equal to v crossed with, let me define a quantity, omega c is equal to q over m times b. And if a charge is moving in a magnetic field, what is this called? This has a particular name associated with this. This is called the cyclotron frequency. So this is called the cyclotron frequency. It's actually angular frequency. It also, if something is going in a circle, that is usually a reference axis, correct? So there is a magnetic field coming out of the board. This charge is actually going around the magnetic field. It's a direction. It is not really an axis. It could be here also. Right? So there's a direction associated with it. So I'll make this a vector. Angular cyclotron frequency is usually a scalar, but I lifted it into a vector, giving it the direction of speed. That way, this actually can be, this equation can be written as v crossed with omega c. So then there is only one parameter in the problem. Velocity is what we are solving for. Correct. That's a vector equation. This is v cross omega c with this is only having a z component. So this is equal to, so let me remember your v cross omega c. You can think of this as ijk, this is vx, vy, vz, 0, 0, omega c. That's your explicit cross product, and that's equal to in the I hat direction, that is vy omega c, and the I hat direction minus j hat is vx omega c, and the j hat direction plus 0 and the k hat direction. So we have three equations we can write down. The x component, the change acceleration and the x component, change in velocity, the x direction with respect to time, is proportional to actually the y component. The cross product actually shuffles this up. Right? So this is equal to omega c times vy. And derivative with respect to velocity in the y direction is equal to minus omega c times vx. Correct? So there is a coupling here. X component depends on y. The acceleration in the x component depends on the velocity, the y direction acceleration, and the y direction depends on the velocity in the x direction. And the z component is, the acceleration of the z component is 0. Right. Which immediately implies, this is clear, that Vz then, as a function of time, is a constant. Which means that if in our case it starts from 0, right? So it will stay 0. which is equal, so Vz at time t equal to 0 implies the constant is equal to 0. So that implies that Vz is equal to 0. Vz as a function of time is equal to 0. Which means that this charge always moves in the plane. It doesn't come out. It was possible that it will come out if you did not have this initial velocity to be 0, if there was the initial velocity to begin with, then it will constant, like it in a linear motion come out, so this will take a helical form. It will still be circular, but it will actually become a helix. Like it will come out, it will drift in one direction. So that's possible, but we are doing the simple scenario where expectation is that this will become a circle that we haven't shown. So this is kind of decoupled completely. We only have x and y component. So let's put the x and y components together. So dvx over dt, actually substitute x, substitute the second equation in it, x, vx to be substituted in there. So when I substitute that, so I get second derivative of vy over dt squared is equal to, so that is a minus omega c. So that's minus omega c squared times vy. And if I were to substitute vy in this, I also get second derivative of vx with respect to dt squared is equal to minus omega c squared times vx, right? So that way they decouple now. We have, if you put one in the other, then we are able to see the, we are able to separate the equation into two. Right? So that's two differential equation, but that's a differential equation we know how to solve. What is the solution for this? If you have an equation like this, what does it mean? Think of a function whose second derivative is the function itself and flips the sign actually. What is a function you can think of whose second derivative is the function itself? Think of elementary functions. Sine and cosine. You take the derivative of sine x, it becomes cosine. But you take the second derivative of the sine x, it gives you back the sine. And in fact, it gives you the negative sign also. In fact, it could be a cosine also. In fact, it could be exponential of I also. So it seems like it could be sine or cosine. And this is a second order differential equation. So it can have two combinations. So typically you say this is A cosine omega ct plus B sine omega ct, because a linear combination of both are possible and they are independent solutions. So usually a second order differential equation has two linearly independent solutions possible. This is an independent equation as of now. So Vx could be C times cosine omega ct plus D times sine omega ct. Right. But we know that dvx, so if we take the derivative of the Vx, we should get omega cy. So let's say this is equal to divided by omega c, then I should get Vy. but I'll take the omega c here. So if I take the derivative, so that's minus c sine omega ct, right? I'm substituting this in here, plus d cosine omega ct, right? Cosine becomes sine with a negative sign. And there's an omega c that comes out, I put it in the denominator. But according to the first equation here, this should be Vy, right? So this should be equal to A cosine omega ct plus B sine omega ct. So I substituted this in here. So equating the two, it is clear. So that implies that C is equal to minus B and D is equal to A. I also have Vx is equal to 0. So Vx of 0 at time t equal to 0, that's equal to 0. That means Vx is C, so that means 0 is equal to, at t equal to 0, so that's C and plus 0. So that implies that C, which also makes minus B, is equal to 0. What about Vy is equal to J? So Vy at time t equal to 0 is V naught. So that's V naught is equal to A plus 0. That implies that A, which is also equal to D, is equal to V naught. That actually solves for all the constants here. So what we have is Vx as a function of time is equal to C is 0, so that's D is V naught, so that's V naught sine omega t. And Vy as a function of t is equal to A, which is V naught cosine omega ct. Which makes sense. Notice that if you were to set time t equal to 0, x component is 0 right here. One thing is immediate, that if I were to solve for this implies, right, Vx squared plus Vy t squared is equal to V naught squared, right? So the magnitude of velocity remains the same, which is a signature of circular motion. We still don't know whether it's circular motion, but this is a typical signature of uniform circular motion. Is that clear? Any questions? Okay, so that's velocity. We can do position, right? So this is dx by dt, right? So integrate this, we can get time. So this is V naught. So if I integrate sine, I get minus cosine, right? So that's minus V naught over omega c cosine omega ct plus some constant, right? So let's call it x naught. And similarly, y as a function of time, that's equal to plus V naught over omega c times sine omega ct is plus y naught. Again, we have x at time t equal to 0 is equal to 0 because it starts from the origin. At time t equal to 0, this is cosine is 1. This is 0. So we have 0 is equal to minus V naught over omega naught plus x naught. That implies that x naught is equal to V naught over omega naught. And y of 0 is equal to 0, which is equal to 0 plus y naught. So that implies that y naught is equal to 0. So we have our equations of motion to be x of t minus, I put x naught onto the left, so that's minus v naught over omega c is minus v naught over omega c. Let me define v naught over omega c, dimensionally speaking. That is going to become the radius of the circle. So let's say this is r is equal to minus r cosine omega ct, and y as a function of time minus 0 actually is equal to r sine omega ct. If I were to put this together, it's clear what is happening. If I were to square this, x of t minus r squared plus y of t minus 0 squared is equal to r squared, which is an equation of a circle which is centered at, so center is at the coordinate r comma 0, and radius is r, which is equal to v naught over omega c. Which makes sense. So that's your center, r comma 0, and if that's the center, then it is also the radius also, right? So that serves the purpose of the radius and the center. This can be, usually this is done geometrically, that's perfectly fine also, but it's good to see this algebraically coming out as a solution. Okay. Helps. I hurried up in the end because I was short time, but it's clear.
Yeah. Yeah, the cosine sine connection with the derivative there is just took me a minute
Okay.
to see.
Even this one, like when I went from here to there.
Actually, at the very top right, it was just
So is this clear from here to here?
that's where I'm kind of.
Okay. Okay. Now the point is, why is that? If you have a second order differential equation, you can have two independent solutions.
Yes.
Okay. So you just have to find any two solutions that satisfy this. That's one way of going about it. So you ask for which is a solution, but there are many solutions, exponentials of solutions also of this. You just have to pick two of them which are independent. Now you ask, what do I mean by independent? Right? How do I check that the two solutions are independent? And that involves a quantity called the Wronskian. So Wronskian of two solutions. So if, for example, if I have cosine omega ct and sine omega ct, right? I take the derivative of that, in this case with respect to time. So this is minus sine omega ct, and derivative of sine is cosine omega ct. Is that clear how I proceeded on that? So write that as a determinant of course. So write the two solutions in the first row and write the derivatives in the second row. Right? Solutions, solution 1, solution 2, derivative 1, derivative 2. And there should be an omega c in front of it. And then take the determinant of this, cosine square, minus sine square, because there's a minus, there's a plus, so this will become just omega c. If this came out to be 0, that means it is dependent solutions. They are not independent. If this is not 0, that means they are independent solutions. So that's how you typically check. Where else? Like oscillations, when you do harmonic oscillations, that's the same idea here. Typically, what is done is that there is a prescription to get this or put in an exponential. But those all work only for some straightforward equation. Like this is a straightforward equation, but I don't want to give the impression that if you have a differential equation, there's always a way to proceed. You don't have such a thing. Usually what you do is, do you know any solution? Look for this. Typically it is trial and error, like you try for solutions and figure out what the solutions are. And then you find out, oh, what is the second solution that's there? Of course, with a lot of experience. And once you have the experience, then you say that, oh, in general, a second order linear differential equation can be solved in some manner. Right? So that's how. So is that, was that your question?
Yes, Asher, thank you so much.
Yeah. Okay, any other comments?